So next class will be on steel. We learned about crystals. So the question is, are the crystals perfect? So we learned that metals, they have crystalline structure. It turns out that a very perfect material is only a very tiny material. So if the materials are if you look at just a very tiny portion of the material, it may be perfect. It may have the theoretical strengths and the theoretical stiffness that you learn based on the interatomic forces. But as the size grows, materials have defects. And even in crystalline structure, there are different kinds of defects. They can be a point-wise defect, linear, areal, or volume. We want to today learn about these different defects and see how they affect the engineering properties. So basically, this is what we want to learn today. So only when we have very tiny, so I've written this down tiny, just that you remember, if you have just 1 micron of material, maybe it's perfect. If it gets bigger, then you are going to have some issues. So, point defects. Point defects have different there are different types of point defects. One is when an atom is just missing in the crystalline structure, like a vacancy. Sometimes an atom of the same type kind of comes in between the space of the other atoms, and this is called self-interstitial defect. And sometimes you have small atoms, they come in the space between the other atoms. This is kind of impurity. And sometimes an atom of a similar size comes and sits in the crystalline structure of a different material. So we have different sorts of point defects. And you will see soon that alloying is pretty much point defects. So you have some other atoms inside your crystalline structure. I will talk about that. But typically, point defects are not going to cause too much trouble. A very important type of defect which causes a lot of trouble in metallic structures is dislocation. And dislocation is when, for example, here you can think about one line of atoms missing, or you can think that on the upper side there is an extra line. Either way of thinking about dislocation is correct. The problem with dislocation is that then on this plane you are going to have a slip. And this is behind a lot of properties of the metallic materials. So dislocations are linear defects, and you can think about them as an extra line of atoms or a missing line of atoms, as you can see here. They can be edged just like that, but they also can have some distortion associated with them. Sorry. As you see on the right-hand side. Now, what is very important for us, these are different representations, is how dislocations affect the material properties. And for that, it's important to see what happens when you apply shear to a metal which has dislocation. When you have dislocation here, basically you have weakness. So when you apply shear, the plane, like the atoms jump one step at a time. And as you can see, if you start here, after a while, you are going to have a large deformation. But it doesn't happen immediately. It happens one plane at a time. So that's like the analogy with the caterpillar, how it moves. It just carries itself up and then it goes one little tiny step at a time. And dislocation kind of moves inside the material very slowly. And this is what gives the metals their ductility. Dislocation is actually behind a lot of, so it's written here, the plastic deformations of the metal is caused by dislocation, and this is called the slip plane because they facilitate the movement on this slip plane. So the atom moves one step at a time, and then before you know it, you go from here to here, where you basically have a displacement. So dislocations are very important. So we said we have point defect, linear defect, areal defects. Areal defects are pretty much grain boundaries. Last time we talked about single crystals versus polycrystalline materials. So when you have polycrystalline materials, you have grains, and the boundaries between the grains, that's when you can develop defects. Normally, they could be weaker than the grains itself. And these are some microscopic images. Like even if you look at aluminum or steel, this is how it looks like under a microscope. You have grains and you have boundaries. And you can have precipitants and defects along these boundaries. And this is the area kinds of defects. And why they happen? Because when you have nucleation, when you have multiple grains, so from the top part, when you have different nucleation, it may occur that everything is perfect, so this is the top part. I can actually show it here. So this is like perfect grain growth, but then you may have situation where the growth is not it's not perfect. So whether the grains are bigger or larger, as you can see here or there, or may the direction be different. And in these situations, you develop defects along the boundaries, as you can see. Just that you kind of get a sense, those are cartoons, really this is how it looks like. You are looking at a steel on the right-hand side, and brass, I think, on the left-hand side. So you see how the grains look like, and you have all these boundaries. And finally, the volumetric defects are kind of voids that you may have, the volumetric voids that you may have in the structure. And this is also an SEM image of a low carbon steel where you have voids, as you can see in the image. There's some empty space. Okay. Now, what is important for us is how the microstructure affects engineering properties. This is what we care the most about. Unlike brittle materials that we have seen before, like glass or concrete, metallic materials are actually very good in tension. They are, we can stretch the bonds between the atoms. They are very good in tension. They don't break easily in tension, but they're weak in shear. And we want to see why. So if you apply force and it is not very large, you just stretch the bonds and everything bounces back when you remove the force. You have elastic deformation. If you increase the force beyond a certain level, this doesn't happen any longer. So if everything goes back, you have elasticity. But if you apply a lot of force, then it doesn't go back to where it was. So if you compare the first row and the third row, it's not the same anymore. And the reason is basically the movement inside inside the metals, which causes a slip. And this is called, this is really caused by dislocation. We want to look at this a little bit more carefully. So, during the elastic regime, everything is elastic, goes back to where it was. If you go to the plastic regime and you had a microscope, you see that actually you have a slip along dislocations. It doesn't go back where it was before. So you saw how the dislocation was moving. So at some point, it has caused a displacement. So it doesn't go back to where it was before. So the question is now, I just told you that metals are perfect in tension. Everything is, they are much more resistant. But we also learned before that if you apply tensile stress, I showed you even a video, you could see that the coupon becomes longer and at some point creates necking, and then you have actually rupture. So how come then? If they are so good in tension, what is actually happening? Why they are failing in tension? The answer is, even when you apply tension, what is happening at atomic level in the microstructure is not really tension. What is happening is shear. So you can see here that even when you apply tension, when you apply tension, the breakage type is actually shear. So ductile materials, like metals, they always fail in shear when the two planes slip past each other. And this is how they fail, even when you apply tensile forces. Any questions so far? And if you have a microscope and if you can look at the after rupture specimen, you actually see these slip planes. You see that the mechanism is actually shear. It's not in tension. So this is kind of a very important thing to remember about metals and the difference between ductile and brittle materials. Brittle materials are very weak in tension. They develop cracks and break. But metals, they shear, then you have plastic deformation, shear, shear, shear. At some point, they break. And dislocations play a very, very big role there. Now, what happens if, for example, we have dislocation? So again, dislocation moves as you are applying shear, one plane at a time, but eventually you are going to go from here to here, where you can see that there is a displacement, there is a slip. So if you have dislocation, what happens is that if you apply just, let's say this is a dislocation, right? They don't really align, and these, you can think about this as the extra line. If you just apply a little bit of a stress, this is okay, in compression, and release, nothing bad happens. The dislocation moves a little bit, but the stress is not enough to move it from one atomic spacing to the other. It is not enough to make it a slip. So you still have elastic deformation. So this is when everything is elastic. What happens if you increase the load? So think about the caterpillar slide. If you increase the load, then it slips. And when it slips, so you start from here, you increase the load, the orientation has changed, the dislocation has moved. It's not at the same location anymore. Now, if you unload, dislocation doesn't go back to where it was. And this is when you have plastic deformation. You don't have recovery. So it's important to understand how this affects the behavior. So here we have partial recovery, so you have some plastic deformation, permanent deformation, because of the dislocation. So when we look at the stress-strain diagram, so this is a strain. A lot of times you have dislocations inside the material. I mean, our materials are not perfect. So what happens is when you go towards plastic deformations, they actually, you have these slip planes and you have these movements which cause these plastic deformations. So it is actually the cause of plastic deformations in engineering materials. It's very important concept. What is the significance of point defects? I just told you that basically alloying is kind of introducing defects to the crystalline structure. So if you have a pure crystalline structure, all the same atoms, the rupture occurs at the slip plane, and the ductility, it depends on how much you can actually stretch the bonds without breaking. So as you can see here. Now, if you have, imagine that you have some point defects. So I call them defect, but this is like alloying. You have added carbon to iron to make a steel. So the crystalline structure is not as uniform as before. You have here some other atom. It turns out that then when you shear the material, it's not as easy for it to rupture. So alloying makes the material stronger but less ductile. So this is kind of a funny analogy. It is like going over a bump when if you ever drove a tractor, which I don't know, I never did, but it apparently feels probably very hard if you go over a bump on a tractor. Has anyone driven a tractor to confirm this? Yes? Is it like that? Okay. Fair enough. Anyway, just that you remember, when you make alloys, this is kind of in microstructure. You have heard the word alloy, adding other atoms to your crystalline structure. In microstructure, it is pretty much like adding some other foreign atoms inside your crystalline structure. Now, depending on the anode, this could be of the same size, or it could be smaller, it could be of comparable size. And what happens is typically you have higher strength, so the strength increases. Just because it's hard to go over that bump. Just think about that. But ductility normally decreases. Just because it doesn't let these dislocations, it doesn't let this slip to happen. And that is behind the ductility, right? So movement at a slip plane is behind the ductility. It prevents that movement, increases the strength, at the same time ductility goes down. So if you add, if you look at these different alloys, you see that the strength has increased because alloying hinders slippage. Increases strength and you have less ductility. This is the same kind of concept, just presented differently. So the blue curve shows you how the strength is changing with increasing the percentage rate of the alloying substance. Now here in this case is nickel. The red curve shows the elongation or ductility. So this elongation percentage at failure, this is very related to ductility. You see that it's decreasing. Okay, there are some limits, of course, you can see. If you go beyond a certain limit, then it changes. But normally we are in this range where the strength is increasing and ductility is decreasing. And why do we care so much about alloys? Because one of our most important materials, steel, is an alloy of iron and carbon. And look at this graph is very important to understand. What we are looking at is a stress strain for different types of steel. And the percentage that you see is the percentage of carbon. What do you see? When you look at this graph, what information is this of? Does anyone want to describe this graph in a sentence?
Less carbon, more carbon.
Exactly. And higher amount of carbon? Yes, but we see something else also. So as Dimitri said, if you have less carbon, you have more toughness, more ductility. You can see as you decrease the amount of carbon, the ductility increases. But what else do we see? When you increase the carbon, what else is increasing? The strength. Everyone is saying it's a strength. And look at here. We have terms to describe the steel. Like when you talk about mild steel, it means that the percentage of carbon is low. Then you have medium and high carbon steel. So if you are talking about a high carbon steel, it means that it has a high strength but low ductility. And what is that? So there is a trade-off between a strength and ductility when you make steel alloys. I really like this diagram, so I hope that everyone pays close attention to this diagram. I think the last discussion here is, okay, now that we learned so much about microstructure, how can we use that to achieve the types of properties we want to have? For example, how would you have stronger metals? Because if you have just pure iron, it's pretty ductile, but it's not as strong enough. So what do you do to have higher strength? There are three methods. One is alloying. We just learned about that. But there are two other methods. You have learned about the strength hardening before. The other method, which also is important, is grain size reduction. Grain boundaries also prevent the slip from happening. So if you manage to have a material with a smaller grain, then you increase the strength. So remember, rupture has something to do with the slipping. So grain boundaries prevent the slipping. So if you have many of them, you can increase the strength, but you lose ductility always. Now, one way to do that is quenching. And quenching is when you make the steel, for example, you cool it down very fast. So you don't let the crystals, the grains grow. So they have to cool down very fast, so the grain size will be very small. The opposite of quenching is annealing, when you let the steel to cool down very, very slowly, and you have larger grain size and more ductility. Remember that the strength and ductility is always a trade-off. So this is one method which may be new, and the reason it works is that you basically, with having more grain boundaries, you restrict dislocation motion. We just talked about alloy. If you want a higher strength steel, go for the high carbon steel. It has higher strength at the cost of having low ductility. This is what happens. So as the percentage of carbon in the steel increases, strength increases and ductility decreases. And another way of increasing, you have learned this before, is a strength hardening. To increase, if you apply stress, then you increase the strength, and this is what we have seen before. I know time is up. Okay, so there's just this quiz that we can start with next time, and I don't go through this, but to review, please look at. Now, I'll upload the homework, but because I was sick on Monday, the homework will be due Monday, exceptionally. However, there is a video in problem number 1 that I want you to look at. It's about 45 minutes before coming to the class on Friday. It's about the steel production. I think it's a good idea to look at the video. But I'll send you an email with all this information.